Okay, so I think we're good to get started. Before we get going for today, I did this morning post the cover page and the formula sheet for the test, so if anybody wants to use that while you're studying, it was there. I was second guessing myself a bit, maybe the test was too long, so I made one of the questions shorter, so it shaved off a couple of minutes for me, so hopefully you won't find it very long at all. Maybe it's too short, but anyway, I'm not going to make it longer now, it's gone to printers. So are there any questions before we get started? Same deal as the last test. Make sure you don't forget your calculator. I can't say I'll have spares, so you may wish to have one. So on Monday, we finished up our resistor circuits. And there's our summary there. And today we're going to start our C circuits. So this very packed slide is a review of everything we've done with capacitors and resistors, more or less. This one doesn't have Kirchhoff's laws on it. They could maybe go in there as well. So we know that capacitors store charge, they have potential difference across that. We know how to add series and parallel. Resistors dissipate energy. We know how to add series and parallel. Next, we're going to look at circuits where we put the two things together. So one circuit with both a resistor and a capacitor. We're going to look at that behavior. It's going to be a mix between qualitative and quantitative. I think the most important thing to take away is the behavior of how the circuits work. We won't really go heavily into the math, but we will do some numerical examples. So when we have circuits with resistors, we know that we have current, or we have circuits with steady currents. And the size of that current is essentially controlled by the size of the resistance in the batteries. When we have capacitor circuits, we only have charge flowing for a little tiny bit of time. So that's when they get charged up, and we'll see also when they get discharged. So this one has a steady current, this one has a changing current, and when you put the two of them together, that's when you get a lot of interesting applications. And we'll talk about some of those too. So this is where we're going. So a task I'll give you for homework is figure out the units that you get when you multiply resistance and capacitance. So when you multiply an ohm by a farad, you should be able to work out that that's equal to seconds. I'm going to leave that one for you for a homework project. And we just want to take a look. This FET simulation is not bad for looking at what happens in these kind of circuits. So I'll start with nothing connected. I've got a capacitor here. I've got a light bulb here. The light bulb is going to act like a resistor. And then my battery here is my source of potential. It's a battery. So if I want to change capacitance, I know that I can change the size and, well, I could change the shape, but I could change the size and the plate separation. And this digit up here gives you the capacitance as you change those. So if I make my plates very small and very far apart, we get a small capacitance. If I put them close together and really big, we get a big capacitance. This is things we looked at in our capacitor section. The first thing I'll do is I'll take my capacitor and I will hook it up to the battery. Okay? So there's what that looks like. We hook it up, the charge flows, our capacitor gets charged up. We've got positive on one plate, negative on the other plate. We can look at the electric field if we want to. So these are things we can do. So this is stuff we have already looked at. I think I'll make my plates pretty big. Now let's look at what happens if we connect it to a resistor. So we'll disconnect the battery, hook it up to the resistor. Remember, my resistor is a light bulb. And the light bulb lights up. And you see that the charge decreases, and eventually the light bulb goes out. Okay? So this is what happens in a real circuit. You can change stuff. If you make your capacitance really tiny, so I'll make my capacitance as small as possible, charge it up, move it over to the light bulb. That one dies out really fast, so it lights up only for a short time. Now if I put my capacitor plates close together with a big area, that gives me my maximum capacitance. Now I hook it up to the light bulb, and it takes a long time for all that energy to dissipate. So these are the things we're going to look at. How long does it take? And what's happening in the circuits over time. So all good there? If you Google FET capacitors, it'll take you to this page, and you can look around at that a bit if you wish. So we're going to ask what happens in our circuits with both resistors and capacitors. Not much to add on this slide. So the R part of the circuit provides a steady current. The C part of the current circuit, we get a current only when charging and discharging. So first we're going to look at a charging circuit, then we'll look at a discharging circuit, and then we'll try and work some examples in how we go. One thing we're going to look at is how long does it take to charge or discharge and what sorts of things matter in those circuits. So we'll do the charging capacitor first. So in a typical circuit where we want to charge up a capacitor, we take a capacitor, initially it's completely uncharged. We put it in a circuit with a supply of potential like a battery and a resistor, and we put in a switch that we can open and close. So that's a typical kind of charging circuit. So let's go through the nitty-gritty, what happens over time. So initially, time less than 0, we have our switch open. If the switch is open, nothing interesting is happening. Okay, so at the very beginning, there's no current, because current can't flow through that open gap there. And the capacitor is uncharged. So we took it out of the box and it is not charged up yet. So that's where we begin. Next, at t equals 0, we take that switch and we close it. So we bring it down like there, we complete the circuit, and now current is allowed to flow. T equals 0, we close the switch. So let's think about what happens. Now I have a connected circuit. Now the chemical reactions in the battery cause the positive charge to flow. Positive charge comes out of the positive end. That's our current flow. So we close the switch, current flows. If current is flowing through our resistor, this would be the positive end, this would be the negative end, so we'll go from high potential to low potential. We're thinking about what's happening to the potential in the circuit. We've got current flowing through a resistor. You know, Ohm's law tells us there's going to be a potential difference across the ends of the resistor. Delta V of the resistor is equal to I times R. And at the beginning, I'm just going to do the next part first. The potential difference across the ends of the capacitor, so right at t equals 0, that's as soon as we close the switch, we know over time that all the positive charges will build up on this plate. It will drive them away from the lower plate. Over time, this one will get charged up. But right at the beginning, there's no time for it to get charged up yet. We've only just started. That tells me that there's no charge on the plate yet, so there's no potential difference across the capacitor yet. So delta V across the capacitor is equal to 0 because the capacitor is not charged. Let's think about what that means for the delta V of the resistor. So the battery puts in a potential epsilon. None of it is across the capacitor, so all of it has to be across the resistor. Because the amount of potential we put in is the amount of potential we use up. Then we might recognize that that means that this current is going to be a maximum. So our initial current will be the biggest because V equals IR, V is the biggest, makes it the biggest. Okay, so that's what's happening right at the very initial bit. What happens some little bit of time later? So for t bigger than 0, as time passes, the switch is still closed, the current is flowing, charge is starting to build up on the capacitor plates. So at t bigger than 0, the capacitor will carry a charge. That we'll call Q. Okay, so some charge is building up on the top plate, which has charge on the bottom plate. So it's starting to charge up. We'll call that amount of charge Q. That means that the potential difference across the capacitor would be that amount of charge divided by the capacitance. It's just our equation for capacitors. So we know how much potential is on the capacitor. We know that current is flowing in the circuit. We know that the current is related to the charge because current is change in charge over change in time. So the current in the circuit is I equals change in current dQ divided by change in time dt. I'm going to put a plus sign in front. This plus sign is reminding us of the fact that we're getting current in this circuit because we're adding charge to the capacitor plates. So this current is flowing and it's charging up the capacitor. It's increasing the charge on the capacitor plates. So that's our current. If that's our current, then we can figure out our resistance, our potential across the resistor. The delta V of the resistor is the current times the resistance. Everybody okay with the steps of what happens? Okay, so that's physically what's going on. That's our description of it. If we'd like to put it together and think about what happens to the current and the charge over time, let's apply the potential law and see if we can figure out descriptions of what's happening with current and potential. So we want to write Kirchhoff's potential law. So that means we take a loop around our circuit. We know that the net potential around the loop, delta V of the battery, plus delta V of the resistor, plus delta V of the capacitor, all has to equal to 0. So there's our potential law. The delta V of our battery is plus epsilon, where our battery supplies a potential or an EMF. For our resistor, we have a potential drop, so it's minus, and that potential is I times R. Our capacitor, again, we have a drop because we go from plus to minus. Q over C equals 0. Are we good here? I don't think you would solve this equation in Math 1001. I'm pretty sure you wouldn't. I think this might be a Math 2000 equation you would solve. So what I'm going to say is let's solve the equation. And if you're interested in that sort of detail, this is the kind of thing we will certainly solve in Physics 2055 when you're doing that math concurrently with the physics course. In the meantime, I will just give you the solution for it. When we solve this equation, we have to remember that I is dq over dt. We put that in here. We've got to solve that equation. It gives us that the charge, as a function of time, is the EMF times the capacitance times 1 minus e to the minus t over r times c. So there's the solution to that equation. If you've done some extra math, you might be able to go ahead and solve that. That's not something I would ask you to reproduce on a test or an assignment, nothing like that. So the details in this equation, first of all, this symbol E, that's Euler's number. How many people know Euler's number? Some, solid few. Euler's number is one of those special numbers like pi. This one has a value of 2.71828, So that one never ends, just like pi never ends. So that's one of those special numbers that we have. So it's this number to the power of negative t over r times c. R is the resistance, c is the capacitance, t is our time, E is the EMF, and c is capacitance. So the EMF of the battery times the capacitance, that would be the maximum charge on the capacitor. Typically, we give that a symbol of Q0. That's the notation from your textbook, so I'm gonna stick with that. If you talk to other people in the help center, they might give it like a Q maximum or something different, but your book uses Q0. So that deals with that bit. Last, this RC in the bottom here equals a new definition equals the symbol tau, which is what we call the time constant. And this is what Monday's group did in the lab this week. I'm not sure if Thursday's group will have this lab yet or not. I think not tomorrow. Yeah, okay, so you're gonna see this in the lab tomorrow.
Yeah.
No, it's good, it's neat. Okay, not too much excitement for the lab. That's okay, you don't have to be excited. Okay, let's put this together in this equation. This gives us the charge on the capacitor as a function of time is this maximum charge QO times times 1 minus e to the minus t over tau. So when we have a capacitor, which is getting charged up, this is how we find the charge at any specific time. And we're going to look at the graph of this, and hopefully we'll get a little bit of a better visual. If our t is equal to 0, it gives us 0 charge on the capacitor. If our t gets really, really big, that number goes away and we get our maximum charge on the capacitor. So this describes the charge on the plates as a function of time. If we use our relationship, I is the derivative of q with respect to time, what we get is that our current I is equal to I0 e to the minus t over tau, and that I0 is the maximum current going through the circuit, which would be the potential divided by the resistance R. And in this relationship, if we put in t equals 0, we have our maximum current, so current flows really well at the beginning. Over time, as t gets really big, it's harder and harder for the current to flow, so the current goes to 0. When the current goes to 0, that's how we know the capacitor is all charged up. If you think physically about what's happening, every time we dump a new charge on this plate, it's harder to put more charge on. It's repelled by what's already there. So over time, it gets harder and harder to charge up, so eventually it stops charging up. Last, a way to think about this, some people like this approach, some people not so much. If your capacitor is completely uncharged, so right at the very beginning, this capacitor acts like a short circuit. It acts just like a piece of wire. It's easy for current to flow if it's uncharged. That's because it's easy to dump charge on. When your capacitor is completely charged, that means current can't flow anymore and it acts like an open circuit. So some people like to think about the circuits that way. If that works for you, you can totally go ahead with it. Okay, questions? Okay, so that was a deeper description of what happens over time. Let's do a graph. If you downloaded the notes, you have something that looks mostly like this. I wasn't very happy with it, so I tinkered just before class. So I drew in a table, and I just made this graph a little bit longer on the time axis, but it's still basically the same thing that you have. So let's think about making a graph of the charge as a function of time. So we want to graph our charge as a function of time versus time. So we want to make that graph. Let's just write down our equation for the charge. Q is equal to Q0 e to the 1 minus e to the minus t over tau. And then tau is equal to R times C, our time constant. QO is our maximum charge. That's equal to the EMF times the capacitance. And we already said that our behavior as a function of time is it starts with no charge and it ends up fully charged. So that's what we're going to expect to see in the graph. Let's use this equation to figure out the relative fraction of our charge over time. So let's use this equation. For our first value, so in this table, I'm going to put t here, and I'm going to put my charge as a function of time in this column. So let's do what happens at t equals 0 first. So if t equals 0, our charge, Q of t, is equal to QO times, I'm putting a stray e up here in this equation. I have no idea why, but I scribbled it out now. You should do likewise. QO times 1 minus e to the minus 0 divided by tau. So something to an exponent of 0, that's equal to 1. So we've got 1 minus 1 here is equal to 0. So the first point on our graph is at 0 and 0. So there's our first point. For our next point, instead of putting in a number for t, I'm going to say what happens when t is equal to 1 time constant. So 1 times r times c. So t equals tau, which is equal to r times c. In this case, our charge at that time is QO times 1 minus e to the minus t, or minus tau over t. So QO to 1 minus e to the minus 1. So that would be a thing you could figure out on your calculator. What you would find is that 1 minus e to the minus 1 is equal to 0.63. So after 1 time constant, our charge has increased to 63% of the maximum charge. Right about here, we're at 0.63 QO. Okay, let's go to 2 time constants next. So 2 times RC. So our charge is equal to QO times 1 minus e to the minus 2 tau over tau, which would be QO times 1 minus e to the minus 2. You could do that one on your calculator, and this number, 1 minus e to the minus 2, would give you 0.86. So after 2 time constants, we hit 86% of the maximum charge. Okay, 3 time constants. We're not going to do this all day. We get Q of t, I won't write in all these steps anymore, equals 0.95 Q0. Okay, next we'll do 4 time constants. For that one we get 0.98 Q0, so we're almost fully charged. So on our graph here, I'll put in 4 tau and 5 tau. So after 4 time constants, we're up here to 0.98 Q0, or 98% of the full charge. And then after 5 time constants, Q of t is equal to 0.993 Q0. So 99.3%, almost exactly at the line. And what we say at this point is that we're so close to the maximum charge, we call this fully charged. Okay, so it's an approximation, but it's not a bad approximation. So at this point, at t equals 5 tau, we say capacitor is fully charged. Here's kind of a theoretical question. Could you actually really ever get to fully charged? No, you couldn't really get there, right? In practice you can, because who can tell the difference between 99.99999% and 100%? Nobody, right? You defy you get into the range of uncertainties on your meters, right? So you can never actually get there, but we're okay with close enough. Questions? And then this Q0, of course, is the maximum charge. Yeah, we wrote that up here. Okay. So, yesterday on Brightspace, I put an announcement up with a couple of new slides. We're gonna look at one of those new slides right now. Okay, this page has a lot on it. I recognize that it has a lot on it. You probably are not gonna wanna copy it all out. So right here is just a typed up version of what we wrote on the last slide. I just wanted you to have it nice and neat in your notes for if you went back to it to study. So let's take what we just talked about. Let's give ourselves a value of potential, a capacitance and a resistance. Let's say that the switch closes at T, and let's ask some questions about what happens over time. So this is kind of a simple example, but I think it's not bad to go through anyway. So let's start with part A, and I can just put the paper side by side and get most of that here. So part A talks about when the switch closes. So when our switch closes, this thing comes down, and our switch is connected. Current is allowed to flow. Initially the current's at a maximum, our capacitor is not charged up yet. So this is right at the beginning. When the switch closes, what is the potential across the resistor? Part A. This is at T equals 0 because the switch has just closed. When the switch is just closed, we want the potential across the resistor and the capacitor. I'm going to answer the capacitor first. Delta V of the capacitor is the charge on the capacitor divided by the capacitance equals 0. So right at the very beginning, no charge has had time to collect. There's no potential across that capacitor right at the very beginning. That means the potential across the resistor has to be the full potential supplied by the battery, which is 1.50 volts. Okay, part B, when the switch closes, what's the initial current through the circuit and what is the initial charge on the capacitor? We've kind of got some of that answered already. So the charge on the capacitor equals 0 because no time to charge yet. For our current, delta V through across the resistor is the full potential, 1.5 volts, equals the current through the resistor times the resistance. So the current through the resistor is the potential divided by the resistance, 1.5 volts, divided by 100 ohms, equals 0.015 amps. This is the maximum current, because this dies off over time. If that's the maximum current, then we can come back and put I zeros on here if we wish. You don't necessarily have to do that, but it might help you keep things straight. Okay, so far so good. What happens to the current and charge, current through the circuit and the charge on the capacitor over time, and what happens to the potentials over time? So for part C, let's do the current first. So the current through the circuit is equal to I0 times e to the minus t over tau. This equation shows us that the current decreases. For our charge, Q is equal to Q0, the maximum charge, e to the minus t over tau. My goodness. I was doing both circuits before I came here, now I've got them mixed up in my head. Q is equal to Q0, 1 minus e to the minus t over tau. There's our equation for our charging capacitor. This one increases over time. Q0 is our maximum amount of charge that we might get, which is the EMF times the capacitance. We weren't asked for what the maximum charge is, but since we wrote down this equation, why don't we go ahead and figure out what that is? 1.50 volts times 1.77 times 10 to the minus 12 farads gives us a maximum possible charge on the capacitor plates of 2.655 times 10 to the minus 12 coulombs. so there's the maximum charge even though it didn't ask for it. What happens to the potential across the resistor and the capacitor over time? So let's look at what happens there. Delta V across the resistor is current times resistance. Our expression for current we have up here, I0 times R e to the minus t over tau. Okay, so I just put in my equation for I right here to give me an equation for the potential across the resistor. If we think about this behavior, when t equals 0, delta V across the resistor equals I0 times R is the maximum potential. If t is a big number, greater than 5 tau, delta V across the resistor is 0. So across the resistor, the potential decreases. So there's a long explanation for something you probably intuitively already knew. Okay, what happens to the potential over the capacitor as a function of time? So delta V for the capacitor is the charge divided by the capacitance. My equation for my charge is Q0, 1 minus e to the minus t over tau. Divide that by c. So there's an expression for the potential across the plates of the capacitor. You might recognize QO over C as our EMF. We could recognize that there. So if we look at this behavior, t is equal to 0, e to the minus t over tau is equal to 1, 1 minus 1, delta V of the capacitor is equal to 0. If t gets big, delta V of the capacitor equals the maximum potential, the EMF, 1.5 volts. So overall, the potential across the capacitor increases. So the potential switches from being all over the resistor to all over the capacitor, so it moves over time. Part D, find the time constant for this circuit. That one's easy, that's just a plug and chug. Our time constant tau is equal to R times C. 100 ohms times 1.77 times 10 to the minus 12 farads equals 1.77 times 10 to the minus 10 seconds. So there's our time constant for that circuit. Part E, how long does it take for the capacitor to become approximately fully charged? In a test, this word may or may not be there. If I say fully charged, I'm not looking for you to be a smart aleck and say never. It means after 5 time constants, so you may or may not see the word approximately. But I do often tend to be a bit pedantic, so it wouldn't be like me to leave it out. But anyway, if it just says fully charged, it means 5 time constants. So T equals 5 tau, 5 times 1.77 times 10 to the minus 10 seconds, to give us 8.85 times 10 to the minus 10 seconds. And I would say that this happens very fast.
Would it be fine if on an assessment we were given that without labeling the amount of time constants, we would just ask? We could just ask someone to clarify how many time constants?
Well, no, you've got to know that it means 5 time constants.
Okay.
Yeah, for sure. Okay, any questions? So, what's one application? One application I can think of where this might be kind of useful would be like your intermittent wipers on a car. So if you had intermittent wipers on a car, seriously, right? The resistance controls the amount of current. The capacitor turns it off and on, so the switch just moves back and forth when you turn it on. So the capacitor gets all charged up, the current is flowing, the wipers go one way. The switch moves, the capacitor starts to discharge, the wipers move the other way. So that's kind of an example of an application. So any place, like any circuit where you have a timekeeping thing, that's an RC circuit. Okay, So that's our charging capacitor. Next, we'll look at the discharging capacitor, which does a lot of the same stuff. It acts a lot the same way. So any questions to clear up before we get going? So in a discharging capacitor, we start with a circuit with a fully charged capacitor. We connect it to a resistor and we put in a switch that we can open and close as we see fit. So here's our circuit for a discharging capacitor. So let's look at the process, what happens over time. So in the beginning, for t less than 0, the switch is open. The capacitor is fully charged. That means it's carrying an amount of charge that we'll call Q0. So before we hooked it up to this circuit, we connected it to a battery and we let it get charged up. So that's what we did at the beginning. There is going to be a potential across the capacitor, delta V across the capacitor. It's going to be the charge on the capacitor divided by the capacitance, and we might call that delta V0. Okay, some places might also call it delta V max. You know, you'll have different people say different things. But this will be the biggest potential because our capacitor is carrying its full charge. Because the switch is open, there's no current flow in this circuit. So let's put that in as well. If there's no current flow, then that might make us think that delta V across the resistor, which is I times R, is equal to 0. Okay, so we might think those things as well. At t equals 0, we're going to close the switch and see what happens. So we shut this guy down. We've got our complete circuit. As soon as we have the complete circuit, we think about what's happening here. We have a bunch of these positive charges sitting on this plate. They're repelled. They want to escape each other, so the charge is going to start to leave the plate. Positive charge is going to start to come off the plate. Positive charge moving around the circuit, that's what we call current I. Okay, so the current is going to start to flow. It's going to come around the circuit through the resistor, and that'll carry on until there's no more charge left on the plates. So at t equals 0, we close the switch. Our initial current, we'll call that I0, that one starts to flow. This current is going to be a maximum. You want to think about why that's a maximum. Initially, we have all of the charge on the plate. There is a large force repelling those charges away, so it's getting pushed off as quickly as possible. So that's why the current is a maximum, because it's desperate to get out of there. With our switch closed, we might ask what's the potential across the resistor. Delta V across the resistor is going to be equal to the current times the resistance. And with our switch closed, if we think about Kirchhoff's laws, the potential across the resistor and the capacitor would have to be the same. Okay, and that would be a maximum. So that's right when the switch closes. Then after a little bit of time, some of the charge is depleted, but not all of it. So after some extra time, and it's still closed, our current is still flowing. So t greater than 0. Our capacitor is losing charge. So that means at some time bigger than 0, the charge on the capacitor plates is less than the maximum charge. A little bit of time later, we've lost some charge. There's not as strong a repulsion anymore, so the current is getting smaller. So our current is decreasing. if we think about potential across the resistors, current times resistance, that has to be decreasing. Potential across the capacitor is charge divided by capacitance, that also has to be decreasing. So if charge and current decrease, then the potential across the resistor and capacitor decrease. Yes.
Two questions.
Yep.
So, firstly, are the delta V's of the capacitor and the resistor equal the whole time from start to finish?
Yes, always equal. Yep.
Which makes sense, because, yeah.
From our potential law, right? So the net potential around the circuit's always got to be zero. Yep. Good insight.
Second question, if this was ideal setup, there was no internal resistance, this would go on forever, right?
Well, that's a good question. So, what happens to the charge? Here's what's going on physically with the charge. This plus right here comes around the circuit all the way through. So think about a little positive charge moving. It hits down here. I've got a plus next to a minus. So now we're one charge down.
Oh, yeah.
Then the next one, then the next one, then the next one. And then there's no charge on the plates at all. So it's not due to a dissipation in internal resistance. It's just that transfer of charge so that we get a net charge of zero on either plate. Yeah, also a good question. Okay. So now what we want to do is find expressions for the charge and the current. We'll apply our potential law just like we did with the charging circuit, and we'll see what we get there. So we want to do our potential law. And draw our loop. Delta V of the capacitor plus delta V of the resistor equals zero. So this is going back to your question about showing why the two potentials have to be the same all the time. Across the capacitor, we've got a potential increase, that's Q over C. Through the resistor, we have a potential decrease, so minus I times R equals zero. Now here's something that's a little bit subtle. We get a current flow because the charge on the capacitor plate is decreasing, so that's kind of important. It's only because Q gets smaller that we have a current flow. So, and current is the change of charge over time, but that charge is decreasing, so it's negative dQ by dt. Okay, just like last time, you could put this in here and solve that equation, or we can just write down our solutions. So we'll say solve. When we solve, we get that Q equals Q0, e to the minus t over tau, and I equals I0, e to the minus t over tau. We'll put those in boxes. And let's make sure we understand what all those things stand for. QO is our maximum current, C times our initial potential, that initial maximum. I0 is our maximum current, it's that initial potential divided by the resistance. And tau is still our time constant of R times C. So both things, charge and current, die off to be zero. So like the light bulb we looked at in the simulation, when we thought about how it died off, the initial potential matters, the resistance matters, and the capacitance matters. Let's do our graph for the decreasing charge, the discharging capacitor. I think we've got time to get through that one. So yeah, like the other one, right before class I decided I didn't like it. So I just made this one a little bit smaller, extended the axis, and I put in a table where we'll calculate the different values of charge. So it looks a little different, but not very different from what you had before. So this is our discharge and capacitor graph. You want to know the charge as a function of time, Q of t versus t. And we know that our charge as a function of time is that initial maximum charge, e to the minus t over tau, where tau is our time constant, RC, and QO is capacitance times delta DO, that initial potential, and that's the maximum. Okay, so I think we can do this one a little bit faster. If t is equal to 0, then Q is equal to Q0, e to the minus 0 over tau, that's just equal to 1, that's equal to Q0. So time equals 0, we have the maximum charge. T equals 1 time constant, Q is equal to Q0, e to the minus tau over tau, or Q0, e to the minus 1. E to the minus 1, if you do that on your calculator, you should get 0.37. So we've decreased to 37% after 1 time constant. After 2 time constants, Q equals Q0, e to the minus 2 tau over tau, e, QO, e to the minus 2. That's equal to 0.14 Q0. So after 2 time constants, we're down to 14%. So it's getting smaller. After 3 time constants, we're down to 0.05 Q0, or 5%. Four time constants, we're getting really small, 0.018 Q0, 1.8%. Right here. And after 5 time constants, we're down to 0.007 Q0, which we say is about equal to 0. It's close enough. So after 5 time constants, we're down to about here. Then if you draw the graph, you get that exponential decrease. So after 5 time constants, we say that the capacitor is discharged. So just like the charging capacitor circuit, you could never truly get to a fully charged capacitor. Here, you could never truly get to a discharged capacitor. Although I guess there's an argument to be said that when your final charge is the size of 1 electron, maybe that's when we could say we're down to our charge of actually 0 because it is discrete. But maybe that's more philosophical than anything else. Okay, we have a couple minutes, but I don't actually want to start the next example. The next one is that second new slide I posted, and I don't want to try and rush through that or break it in half, so we'll quit there. Your test is on Friday. I posted answers to one of the set of practices that went up yesterday, so you know where to find me if you have any questions.